Let's have a look at isomorphic graphs. Two graphs are said to be isomorphic or equivalent if they have the same number of edges and vertices, corresponding vertices have the same degree, or the edges connect to the same vertices. In the first graph, we can see there are 4 vertices and 5 edges, and that's the same in each of the following graphs. The degree of vertex A is 2, it's 2 here, and it's 2 in the third graph. B, 2, the degree 2, and the degree 2 in the third graph. The degree of C is 3, 1, 2, 3, 1, 2, 3, and the degree of D is 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now AD is connected, you can see here. AC is connected, there's AD, there's AC. BC is connected, BD is connected, and CD is connected with corresponding edges. Here we have the same number of edges and the same number of vertices, 4 and 5 in each. Let's have a look at A. A has no connection to B, but notice in the second diagram it does, same in the third one, so that discounts them straight away, but there are other things that are different as well. You can see the degree of A is 2 here, but it's 3 here and 3 here. The degree of B is 2, the degree of B is 2, but over here the degree of B is 3. Can you see some other things that aren't the same? A connected graph is one where every vertex is connected to every other vertex either directly or indirectly via other vertices. Each of these graphs is a connected graph. I can get from A to D via C. I can get from B to A either directly or via other routes as well. So these are called connected graphs. Each of these graphs is not connected. There is no way to get to point B in first graph from C, A or D. Here there's no way to get to D, and in this graph you can't get from AD over to CV or vice versa. Connected graphs can be applied to many applications such as airline routes, communication systems and computer networks, where a single missing or broken connection can lead to a system becoming inoperable. So unlike the bridges in Konigsberg at the start, this is a particular definition. These critical connections or edges are called bridges. So if we remove that edge, it would leave the graph disconnected. You can see that in this graph, it is the edge CD that's the critical bridge, and so if we remove it, we end up with a disconnected graph. The graph is connected if every vertex in the graph is accessible from every other vertex, from any path formed by the edges of the graph, and a bridge is a single edge in a connected graph that, if removed, leaves the graph disconnected. Adjacency matrices contain the information in the graph as a matrix. There are various types of matrices that do this. In this work, we're only going to look at the one type, and these adjacency matrices are square matrices. The rows and columns are headed with the vertex's letters. The integer elements in the matrix record the number of edges connecting each pair of vertices. For example, in this graph we have 4 vertices, so we label each row with their vertex names A, B, C, D, and each column is labeled the same. Now we can see at A there are no loops, so there is no connection from A to A. From A to B there is only one connection, so we enter integer 1 here. From A to C there is only one connection. From A to D there are 2 connections, 1, 2. Now we go to the row B. From B to A there is one connection. From B to B, there are no loops, so no connections. From B to C, there is one connection. And from B to D, well, there is no direct connection between B and D, so we enter 0 into the matrix. Now to row C. Now there is a loop at C, so C to C is 1. C to A, this first element, there's 1. C to B is 1. And C to D, there is no direct connection, so we enter a 0 in the matrix. We go to row D, and here, D to A, there are 2 edges. 2 goes into the matrix. There's no direct connection with B, so a 0 goes in. No direct connection to C, a 0 goes in. And finally, there are no loops at D, and so there are no connections from D to D.